All right, so the entire section is optimizing, uh, well, basically, it's all optimization problems. So, like optimizing your area, your volume, your time, that type of stuff. Like, I think in the test there's an example where maybe, yeah, I think it was, yeah, I think it's the next test. They give you like a piece of sheet metal or cardboard, and you have to figure out, okay, how can I maximize the volume by cutting out certain corners, right? If I cut off a corners, flip the box open, make a container, um, how can I optimize the volume, right? So all these ideas about maximum, uh, the extreme points or maximums and minimums of functions will be applied to something specific. Okay, so we'll start with something simple from the homework. Um, so here we go. Find the length and width of a rectangle that has the given perimeter and the maximum area. Okay, so we got a rectangle and they're talking about maximum. And they're giving us a perimeter equal to 72, I think it's meters. All right, so that's all the info you're getting. So you have to figure out some equations on your own. Take a derivative of the function that they're talking about, right? Because if they mention they're maximizing area, that means they need to use an area equation, take a derivative of area, and go from there. Okay. So if you don't know your formulas, I would print out or write down all the geometry formulas like area of a square, rectangle, sphere, volume, whatever, all that stuff, because you're gonna need it. So remember, so this is coming from your memory, right? This is not given to you. We know that perimeter is equal to 2 length times 2 width, right? Or plus 2 width, right? Just adding the size of the rectangle. We also know that the area of a rectangle is length times width. So these equations come from just geometry, right? Now, eventually we want to use the area formula, but we have everything in terms of length and width. So I'm like, well, that's two different dimensions. I'd rather have it all in one variable if possible. So use the perimeter to help you simplify this guy. So that's what we're going to do. Set this equal to 72 meters and solve for one of the variables. And then you're going to substitute it in here. Okay, so I'm going to solve for length, I guess. Right, so subtract the 2w, divide by 2. Here is my L. I skipped some algebra steps. Do you have any questions on the algebra? Do you see how we solve for L? Okay. All right, so plug this into the area formula. Okay, so this is like my step one right here. Step two, we can create our area formula or equation. A is equal to length times width, which means that's equal to L, which is this, right? Times W. So far, is that okay? Okay. And technically you can reduce this, right? I should have done it up here, but oh well. 2 goes into both, leaving you with, what is that, 36? Excuse me. Minus W times W, giving me 36 W minus W squared. Here we're putting the area formula into one variable. So take a derivative of your area on both sides with respect to width, right? Because it's W's. That means that dA dW is equal to 36 minus 2W. So find A prime. Any question with the derivative step? Okay. So once we have it, we can find the critical number and then determine if it's a max or min, which will then correspond to the original A, right? All right. So if there's no question, I'm gonna turn the page here. Yeah. So here we go. Set dA dW equal to 0. So that gives us 36 minus 2W equal to 0. Solve for W. That should be 18, right? Yeah. This is the find the critical number. We call this step 3. Step 4, determine if it's a critical number. So use the first derivative test, or the second, doesn't matter. Here we go. Here's 18. Pick whatever over here. I'll pick 0. I'll pick 19, I guess. Plug this into your derivative. That's right here. dA dW at 0 would be 36 minus 0. So positive. This should be 36 minus 2 times 19. That's going to be what? -2, right? Negative for sure. Excuse me. So we're going upward and then downward, right? So maximum when the width is 18. So then we have the max of, you want to know the best width and length to make to optimize the area of the rectangle. That's what we're doing. So this could apply to like a fence. Like let's say I want the maximum enclosed area of a fence, and I have 72 meters of material for a perimeter. How should I make my space, right? It's basically what we're doing. So we know that length is equal to about 36, yeah, 36 minus W. So that would mean that this is 36 minus 18. So it just so happens that both are 18. They're not that interesting, but you see how it works, right? We're figuring out the formula for whatever they're asking for, and then we're taking derivatives to find the maximum. That's pretty much it in a nutshell. I mean, any question on this first one? Let me find another example. This is number, on your homework, number 4, I believe. Find the point on the graph of the function that is closest to the given point. So here's the function, and here is the point. Let me show you the graph before we, before we do the work. So you can understand visually what the heck we're doing. So that is the graph that that we're looking at. And the question is, given this random point, -1, 4, right? It's a damn thing. No, I'm sorry. I wrote down the answer by accident. So pretend you didn't see that, right? One sec. It was -5, comma 3 was the point. It doesn't matter. The answer is, how do we get there? So basically, we want to know what's the closest point on this graph here, closest to that blue point over there. Okay. So what we're going to do is optimize the distance formula. Okay. So this distance between 2 points, that formula we used way back when, that'll be the hint, right? So whenever you hear stuff about 2 points, the closest point between whatever, or a graph and a point, or two graphs, most likely you're going to need to do the distance formula. In other words, optimize it. Okay. All right. So do y'all remember the distance formula? We'll call it D. Because this is not given to you. This is something you need to know or have on a formula card.
Is it x2 minus x1 plus y2 minus y1 over 2? No.
Um, yeah, pretty much. It's yeah, x2 minus x1 squared plus y2 minus y1 squared. The only the way I want you to think about it though is that they're not, we have a specific x, right, two and a generic x. Okay, so this is my x1, y1. So write the formula this way for these kind of questions. Write x minus the point in question plus your function y minus the point in question. So this is like my y. Okay. So plug it in, plug everything in. We don't know what x is, but we know what this is -5. We know that this is x minus 1 squared minus 3. There we go. Okay. So this will become, what we're doing is optimizing the distance formula. Okay. So this will be x plus 5 squared plus, this would be x squared minus 2x plus 1 minus 3 squared. Okay. This will become x squared plus 10x plus 25 plus, this will become, I think I wrote this down earlier. I don't want to do that again. X4 minus 4x cubed plus 8x plus 4. Double check everything. Yeah. Okay. Uh, Combining like terms, you get x4 minus 4x cubed plus x squared plus 18x plus 29. Now we don't need the square root. In the book and the homework, they have examples where they completely remove it. Don't really say why, but if we optimize the inside part, that will give us the best. If we find the smallest x inside the radical would not, it would still be the smallest after you square root it. So we don't need to mess with this. Okay. So we're going to work on this formula, find that specific x, then we'll circle back and find the y. We'll optimize Oh, my head's killing me today. All right. We'll call it, I think in the book they call it G of X. Okay. Nice space here. Do you have any questions on the setup so far? All right. So once you have that, find G prime and set it to 0 to find your derivative. So G we said was this mess, x fourth minus 4x cubed plus x squared plus 18x plus 29. G prime is 4x cubed minus 12x squared plus 2x plus 18. So set this to 0. Solve for x. I think we can do grouping or not. Let's try it, I guess. Let's find out. No, I think we'd have to do synthetic division. Hmm. Yeah, I'm trying to find an easy way before I do that. Don't think it exists. No. Do y'all remember how to do synthetic division from college algebra? Second. I need a formula. Okay. Yeah. So you take the factors of the constant term, which would be plus or minus 1, 2, 3, 6, 9, 18. Factors of the leading coefficient would be 1, 2, and 4, plus or minus. Then you divide them out. The possible zeros would be every possibility when you divide them. So 1 divided by 1, plus or minus 2 divided by 1, plus or minus 3 divided by 1, 6, and all the way to 9, 18. But also the fractions, so 1 over 2. 2 over 2 is 1, so we don't need that one. Let me do the ones first. 1 over 4. 2 over 1, we did that. 2 over 2 is 1. 2 over 4 is a half, so we don't need that. 3 over 2, though. 3 over 4. We don't need 3 over 1. 6 over 1. 6 over 2 is 3. 6 over 4 is, what is it? 6 over 4. 3 halves. Yeah, we're good there. 9 over 2. 9 over 4, I guess. 18 over 1. 18 over 2 is 9. 18 over 4 would be 9 over 2. Okay, so we're good. We got every possibility. Usually I start with the simple ones like 1 and -1. Once we get 1, we're good. We don't have to go through all of them. You could, but I'm not going to do that. Let's start with an easy one. 1 divide into this polynomial. So 4, there's no oh yeah, there is. 3, 2, 1, and 0. You start by bringing down the 4. 1 times 4 is 4. Add these up, you get -8. 1 times -8 is this. Add them up, you get -6. 1 times -6 is this. That does not help me at all. So let's try -1. Bring down the 4. -1 times 4 is -4. -12 minus 14. That'll be negative. So -4 be -16. -1 times -16 is a +16. 2 plus 16 is 18. -1 times that. There's my 0. Okay, so that's the algorithm. You did this back in college algebra at some point, one of your algebra classes. You have any questions on going through this one, I guess reviewing this, how we find a list of possible zeros was this step right here, and then using those zeros for synthetic division. So since this is a zero, that means that x plus 1 is a factor, which means that g prime is equal to okay. Real quick, 1 second. Need to verify one thing before we move on. Yeah, this one right here has no zero. So all we got to worry about is this guy. So x equal to, right? This is a critical number, which will minimize g. We should verify, but it's the only critical number, and we are trying to find the closest, which means minimize distance. Any questions so far? Going to the next step. Okay. Technically, we should test x equals to -1. Let's choose these numbers here. So g prime at -2. Excuse me. The hell is that number? Would simply be -2 to the 4th. On this one, I think second derivative test might be better, but it's whatever. It doesn't matter. Oops. G prime was that's not right. This is G. All right, so it'll be 4 times -2 cubed minus 12 times -2 squared plus 2 times -2 plus 18. Yeah. Well, this will be times -8, it'll be -32 minus 24. Nah, that's for sure negative. I don't really care what the number is. Now 0. That would be 4 times 0 minus 12 times 0 minus 2 times 0 plus 18. So 18. And number doesn't matter, so we'll be going down and then up. So like we said, it's going to be a minimum. And x equals -1. Now we have the point, or the x value. So plug that into the original. F of -1 would be -1 minus 1 squared, which is 4, right? The closest point on f of x to the original question was -5 comma 3 is -1 comma 4. That's right. This is our answer here. So we were given this point and the parabola f, and they said, what's the closest point on f to this random point? That's going to be this. Any questions on what we just did? It's the same thing over and over again. We're minimizing or maximizing a function. And that's what optimization means. They ask about an area, a distance, whatever volume. You create the formula or thing they're talking about, you apply a derivative, find critical numbers, and determine if it's a max or a min. That's what we're doing. Does the big picture make sense? I know there's a lot of little details, but in essence, that's all we're doing. Yeah, let me know. Let's do the cardboard box thing. So we have a piece of cardboard that is 14 inches by 10 inches. And we will cut out the corners and fold it up into a box. Determine the height of the box that will maximize your volume. So it always helps to draw a picture. And then remember this last piece right here, right? Max your volume. That's telling you that the volume formula is what we're going to do derivatives on. Okay, so we got to create a volume formula. And we got to use the information that they gave us. Um, so we'll assume some rectangle, right? Cardboard box, flattened out, or piece of cardboard. Has to be a rectangle. May or may not be a square, but it is a rectangle. So we'll say that this entire side is 14 inches. This side is 10 inches. We also know that volume is equal to length times width times height. Okay. Now I want you to picture we're cutting out corners, right? So we got to fold it up. How big are these squares on the corners? I don't know. But you do agree that these equal cuts are going to be what determines the height, right? You see what I mean? Like I cut this out, this will be how high it folds up. So we can call this my H size. That makes sense? Okay. So that would mean that this side is actually 10 minus 2h, right? Once you cut it out. That means that this side is 14 minus 2h. Because I'm cutting out two of them. So that tells us that the length is actually 14 minus 2. I guess I'll use lowercase. Width is 10 minus 2h. Does that logic make sense? Before we go any further, do you see how we cut the corners and why we have these equations here? All right. Okay. So that tells us that we can get the volume formula into one variable. Pretty cool. So the length is 14 minus 2h. Width is 10 minus 2h. And there's my other h. Multiply all that garbage out, and you should get a cubic equation. I'm going to skip that step because I believe y'all can multiply. But let me know the problem. I don't really care. So any questions on finding the volume formula? All right, so all this was to find D. All right, once you have the volume equation, optimize it by taking derivatives, right? So d h of your volume, ddh, with the volume formula, which was for, let me find it. So the volume formula, or derivative, will be this guy. Oh, shit. 12h squared minus 96h plus 140. All right, in order to optimize it, you take a derivative, set it to 0, find the critical number, right? So that'll be 12h squared minus 96h plus 140 equals to 0. In order to solve this, you're going to have to do quadratic formula. So h will equal negative b plus or minus square root of b squared minus 4ac all over 2a, where a is 12, b is 96, c is 140. You're going to get two h's. I'm going to skip that step because it's just take forever. 6.08 and h would be equal to 1.92. So when you use your formula, your calculator will spit out this for the plus or minus. Okay, so we gotta figure out which one gives me the maximum. So at this point, use the second derivative test on both h values. Find out which one's concave down, which would be maximum. And we need maximum for the box, right? We're maximizing the volume. Okay, so the second derivative is equal to 24h minus 96. Second derivative at 6.08 will be 24 times 6.08 minus 96, which will be 24 times that's 49.92, which means concave up, right? Second derivative at 1.92 will be 24 times 1.92 minus 96 be negative 49.92, which is concave down.
A question.
Yeah.
If you know the 6.08 is up, wouldn't that imply that the next one is down?
It should, yeah. Since we're maximizing volume, it should, but we should always check. Since I can't prove that it's
Just,
guaranteed.
just in case there was like a third root that we didn't get or something.
Yeah. Trying to come up with a scenario where like the other one could be like undefined or something, you know, or it could be. I want to say that most of the time, yes, it's gonna be implied, but we should check just in case there's a strange scenario we haven't accounted for. I can't think of one now. I want to say more than likely, but unless you prove a formula, I'm not gonna say yes. Okay, so we got our value. Plug in H equal to 1.92 into the volume, and now we know how much it is. So B, what we found was this guy. That will give us, in the calculator, I'm not going to do it by hand. I believe it was in inches, I don't remember. So cutting out the specific height on the corners will give me the most volume in the box. And this would be the actual amount. Any questions on what we just did? You see the importance of it, right? And why we care about derivatives.
Yeah, I'm moving soon, so I might be able to make some more boxes this way.
Yeah. And it becomes extremely important if you're cutting expensive materials. And I don't want to waste anything, right? That's when we start to care for sure. Or prices, costs, money. We always want what's optimal. And this is how you find it. And when things get more complicated with multiple variables, then you have a you know 5 or 6 dimensional problem. At that point, you need like matrix derivatives in order to do it. But the basic idea stays the same. Find a derivative, find critical numbers, etc. And that's still kind of going to be in the background. No matter how complicated it becomes, that'll be the same. It's just that your functions may become complex. Like, now I'm talking about other classes, not this one. Like if you're doing a maybe calculus 3 or some complex engineering problem or whatever. That's what happens. All right, let me pause it here.